Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline, you'll need somewhere to deploy it, so you should check out Linode. With private networking, shared block storage, node balancers, and a 40 gigabit network, all controlled by a brand new API, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode to get a $20 credit and launch a new server in under a minute. And go to dataengineeringpodcast.com to subscribe to the show, sign up for the newsletter, read the show notes, and get in touch. Your host is Tobias Macy, and today I'm interviewing Peter Mattis about Cockroach DB, the SQL database for global cloud services. So, Peter, could you start by introducing yourself?
Hi, Tobias. My name is Peter Mattis. I am a co-founder at Cockroach Labs, which is the company behind Cockroach DB. I'm also the VP of engineering there. I've been in the technology space for 20 years. Half my lifetime now. I've been involved in data storage for most of that time.
And do you remember how you first got involved in the area of data management?
Well, my first involvement was my job right out of college. I joined a company called Ink2Me, which was making a caching proxy, HTTP proxy. But later on, it involved a much more serious data management when I joined Google in 2002. And at the time, Google was working on a prototype of Gmail, and I was asked when I joined if I had any interest in email and working on this prototype, and I was like, yeah, that sounds pretty cool. And very shortly thereafter, I was put in charge of designing the real backend for the search and storage infrastructure for Gmail, which was quite an undertaking. As you know, Gmail has taken over the world of email since then. My work on Gmail eventually led to working on Google's second generation distributed file system, and that in turn led to some work on Bigtable. Kind of minor amounts of work on Bigtable, but just was generally expanding my interest and knowledge of data management and data storage systems.
I didn't realize you'd been involved in so many of those projects. It's definitely a lot of challenges there in terms of being able to manage data at scale, so I'm sure it prepared you well for the work you're doing with Cockroach. So given that, can you describe a bit about what Cockroach DB is and the motivation for creating the database and building a business around it?
Yes. So Cockroach DB is a distributed SQL database. We talk about using design cloud native database, but generally speaking, it is when we say distributed database, it runs on multiple nodes, horizontally scalable, and it is real SQL. It's not like these NoSQL systems that were the fad a couple years ago and seem to be tailing off a little bit now. This is full SQL semantics, transactions, indexes, all of that. What was our motivation behind building this? We saw some of the genesis of NoSQL. My co-founders and I, we were all at Google at the same time. We saw the genesis of NoSQL inside Google, and they're worried about web scale. They're worried about building these systems. They saw that traditional SQL databases weren't scaling due to their architectures, and there's this kind of adoption inside Google of NoSQL. And then very shortly after that, they saw how much of a burden it put on application developers to give up transactions, to give up secondary indexes. So Google internally started moving away from this quite early on. They started building this system called Spanner. Spanner provides a SQL interface, it provides transactions, and yet is horizontally scalable, very much in the same vein as Cockroach DB. My co-founders and I eventually left Google and kind of looked at the state of the open source distributed systems, and we saw that everybody was still full speed at that time on NoSQL systems. And we saw this disconnect between where Google had been and saw all that burden that was being placed on application developers and what was being developed in the outside and the rest of the industry. And we saw an opportunity there. We saw this pain point of people trying to scale SQL systems, and the pain point there is that you can't traditionally just add more nodes. You have to have the application worry about sharding the database and splitting the data across multiple nodes. And that places a huge burden on application developers. Or you have to give up all the benefits of SQL and go with these systems that don't provide transactions, or they provide transactions in some very limited form. So one of my co-founders actually started developing Cockroach as an open source project, as a side project. And it got enough steam that some VCs were like, hey, you should really do this for real. And we were all very interested in doing it for real. And we knew that if we had a company behind it, we could actually spend much more of our life working on this rather than just doing it as a side project on nights and weekends.
Yeah, it's definitely a product that has a lot of legs in terms of being able to provide that large scale that people are demanding these days as it becomes easier to build a new application and actually have the infrastructure to support a global or, even largely distributed system versus when RDBMSs were initially created, where it was largely the big iron era where you had physical servers that would run the databases. And so in order to scale up, you had to rack a new instance. So
Yep.
it's definitely interesting to see the trends of people moving away from NoSQL and back to the SQL interface because of how well it expresses a lot of the paradigms for interacting with data and being able to store and retrieve it in manners that make sense versus the, document oriented or key value oriented, where you need to do all these backflips in the application code to ensure proper integrity of the data rather than relying on the data layer to do it for you.
And one of the things we've been hearing loud and clear from a lot of customers and users, I mean, they care about scale, they worry about scale, and that naturally attracts them to NoSQL systems that can provide the horizontal scalability. But then they also care about how much burden it is on themselves as developers. We've heard instances of users switching to Cockroach and being able to delete large portions of code because they don't have to do those backflips in the application layer anymore.
The original generation of SQL-oriented databases have typically had difficulties in scaling horizontally because of their architecture. So I'm wondering if you can describe a bit about the way that you've approached building CockroachDB to be able to support that distribution and the distributed ACID transactions that make it such a standout among the available databases.
Yeah, this is kind of a doozy of a question because it gets kind of to the heart of the Cockroach DB architecture. It's a little bit challenging to concisely describe this, but I'm going to do my best. So at the lowest level, Cockroach maintains a key value abstraction, a key value storage layer. And when we talk about this key value layer, the Cockroach provides this monolithic key space. In this monolithic key space, we logically divide it into 64 megabyte ranges of data. Each of these ranges of data is replicated. So given 64 megabyte range, we actually use a consensus protocol called Raft to replicate the data for that range to 3 or more nodes in the system. Raft is this, like I mentioned, a consensus protocol. I don't want to get into all the details of what consensus protocols provide and their challenges.
That's a whole episode on its own right there.
That is a whole episode on its own right there. But one of the interesting things that Raft provides, and all consensus protocols provide, is they provide atomicity of writes. So if you're writing data to a given range, to a single range, that write is atomic. Cockroach builds upon this atomic primitive provided by Raft to build general purpose transactions. And there's a variety of additional mechanisms that come into play there. So in order to provide atomicity for general purpose transactions that are spanning multiple ranges, each transaction has an associated transaction record that is stored on a single range, and we're able to flip the transaction from in progress to either reported or committed with a single write. That's kind of like the very high level hand-wavy description of how we bootstrap atomicity for these transactions. Another part of ACID guarantees is isolation. Cockroach has a variant of locks, which we call intents. All the data inside this key value storage layer is versioned, sort of similar to MVCC, multi-version concurrency control. And this kind of gives each transaction a stable view of the database while other transactions are in progress. Cockroach also, in addition to this kind of MVCC layer, it also keeps track of all the data that's read. And you need to keep track of the data that's being read in addition to the data that's being written in order to provide serializable isolation. And serializable isolation and isolation levels in general are kind of, again, a whole other podcast which we can go into. But serial isolation is extremely important. It's kind of the gold standard of isolation levels. And even like the just somewhat weaker isolation level of snapshot, use these weaker isolation levels, and they're not intuitive to application programmers. And you think that you're doing everything and everything's consistent inside your application, and you get these things called anomalies, and they lead to very serious programming bugs in your system. So that's kind of like a little bit of a whirlwind tour of the high-level architecture. I'd really point any listeners to the Cockroach architecture documentation for more details.
Yeah, I was reading through that while I was preparing for the show, and it's definitely very extensive and well presented, so I'll second that recommendation. And what are some of the trade-offs that were necessary when you were building Cockroach to allow for this capability of georeplication and distributed transactions?
Yeah, so georeplication is kind of interesting. We're talking about georeplication. We're talking about geographically distributed nodes in the cluster. And what geographically distributed nodes implies is higher latencies. So if you're looking within a single data center, a single Google data center, a single Amazon data center, the network latencies can be very low, in the low hundreds of microseconds, which is a microsecond less than a millisecond. We're talking fairly fast to do a round trip between two nodes in the cluster. To put that in, to give you some sense of what those times are, you can actually read from the RAM of a remote machine sometimes faster than you can read from disk on a local machine. So that's within a local data center. But you move to geographic distances and you'll start seeing network latencies of 50 or 100 milliseconds. So much, much slower than reading from local disk, much, much slower than reading from another node at the local data center. So you have to start considering these network latencies both in the protocols used internally inside Cockroach as well as within the application. And this is, we've taken pains inside Cockroach, so you kind of do things in batches and you make sure you do a lot of the work on behalf of a query in parallel. But one of the things that falls out of this is applications also have to be aware of these geographic latencies when they're building a georeplicated system. You're not able to just, do many, many round trips to perform some operation to the database, because each operation of the database in turn involves round trips that involve, latencies that are 50 to 100 milliseconds, and very quickly that adds up into prohibitive query times. The bright side is there are techniques that you can use to avoid this, do work in batches and do it in parallel. Just applications generally have to be aware of this.
And when you were building the database, were you able to stick fairly closely to the sort of canonical definition of what Raft is, or did you have to add your own workarounds or fixes to account for some variances that occur because of these latencies or because of conflicts that arise from having to coordinate these various nodes?
Yeah, so we do adhere to kind of the canonical Raft protocol. I don't even know if there's you call it canonical protocol, but there's a thesis around Raft, and we adhere to it. We actually share our Raft implementation with etcd. It's a library we use, but there's some complications that come up. So when we're thinking about the geographic distances, there are some time settings that you have to put into Raft. Raft is this leader-based protocol, and the leader periodically heartbeats the follower replicas, and those heartbeats have timeouts, and you have to size the timeouts based on your network latencies. But some of the other stuff, some of the other engineering complexities that came up from utilizing Raft, Raft itself provides this abstraction of a log of commands. And generally, you propose a command to Raft does its thing, and then it comes out the other side saying, yes, this command has been committed and it's now stable. And the log is append only. And this is completely general purpose. This is the way a lot of consensus protocols are described, but it's not particularly useful. If you were to try to read a piece of data that was written in a command, you don't want to read through the entire log to find the data that was written. What Cockroach does, what all the other systems that use similar consensus protocols do, is they actually apply these commands to a state machine. And the state machine maintains some state in the system. This is, the commands might say, hey, write key X with value Y, and then underneath you're applying that to the key value storage to write the data. This is kind of easy and obvious, but kind of what isn't obvious is you don't want the log to grow indefinitely. You have to have some heuristics about when to truncate the log. You have to have those heuristics based on when stuff has been committed to log and if the followers are up to date. And those heuristics are kind of non-obvious. There's trade-offs. If you truncate too frequently, that becomes a significant overhead. If you don't truncate frequently enough, your log is taking significant amounts of storage space. A kind of more subtle complexity is how complex the state machine itself should be. Kind of the naive thing, which apparently a number of different implementers have done, because kind of the obvious thing to do is like, I could just make my state machine kind of arbitrarily complex. I can put these commands in, and they can be kind of rich commands, and the state machine can do its thing. But there's this problem that comes up that only really comes up when you get to a production system, which is you want to do software upgrades. And one of the things that kind of an implicit dependency by Raft is the state machine has to be identical. Given an input command, the state machine has to produce identical output on all the nodes in the system that are executing it. And that makes software upgrades kind of fragile if your state machine is complex. To maintain that invariant that, just a small tweak of the state machine that is not actually causing the output to change can get very challenging. We've since moved Cockroach from having a fairly complex state machine to having a very simple state machine model. And this is completely motivated by making version upgrades easier.
Yeah, that's definitely an interesting complication because, as everyone knows, statefulness in a software system is difficult inherently, but when you're dealing with having to upgrade versions, maybe one node at a time, and having differences in the way that the statefulness of the state machine will change the way that the database behaves and achieves consensus that's an interesting complication, and I'm sure one that was
Yes.
Led to a lot of head scratching in the process.
Yes. There's actually kind of one other final thing that we had to deal with Raft. It's not really due to Raft per se, but just our usage of Raft inside Cockroach, which touches back to something I mentioned earlier, which is we divide all the data in Cockroach that's stored in Cockroach into these 64 megabyte ranges. And each of those ranges is a Raft consensus group. So if you go back and look at the Raft thesis, it's just talking about a single Raft consensus group and about the semantics and the correctness of operations upon that Raft consensus group. Our usage of Raft is that we have tens of thousands of Raft consensus groups, and we actually allow these consensus groups to split. And we're also working on having them merge together. But with tens of thousands, hundreds of thousands of Raft consensus groups in a single cluster, there's some bits of Raft that were considered like, oh, hey, this is not going to be a problem if you only have one. One of those is doing heartbeats between the leader and the followers. You have one leader heartbeating each of the followers. If that's all that's going on in your system, it's like, yeah, you can do those heartbeats every couple hundred milliseconds. It's not a problem. But if you have 100,000 Raft leaders, each heartbeating 200,000 followers, the overhead of that becomes quite significant. And it's also kind of strange to see this going on in your system where these heartbeats are occurring even if the system's otherwise idle. So we had to do a bunch of work to allow Raft consensus groups to become what we call quiescent. Quiescent is, if there's no traffic on the Raft group, we stop the heartbeats. And this is more or less safe because we also have another layer that is actually monitoring for node outages. And when there are node outages, we reawaken the Raft consensus groups so that they can start participating in the normal Raft protocol.
And that's interesting. So in theory, you could have a case where you have 3 nodes in a cluster and they each have, maybe 50 shards each. And so there is some distribution of each of those nodes that is a master in terms of the individual Raft groups, but they're not necessarily all going to be on the same node. Is that correct?
Yeah, more or less. I mean, so if you have what you said is shards, we call ranges. You could have these 50 ranges and they'd be on these nodes in the cluster, and some of the ranges, each node would be a leader for some of the ranges and a follower for some of the other ranges. And you can imagine they're just exchanging messages all the time. And they're doing this even when there's no other load on the system. Nothing's being written to these Raft groups. Do they really need to be doing all this work? And the answer is no, you don't want them to be doing all that work. You want some other kind of simpler mechanism to determine if a node is alive or dead. You don't have to have that down at the Raft level itself.
That's interesting. And in terms of optimizations for supporting these geographic distributions and reducing latencies, are there any particular strategies that you had to work in to make that more optimum and easier for people to reason about?
Yeah, I'm not sure about easier to reason about. We certainly, this is an ongoing process. Some of the work that we've done, we've allowed an extended SQL language so that you can, normally when you're, SQL is this kind of interactive protocol where you begin a transaction, then you do a series of statements. And the normal way to interact with SQL is you say like, hey, I want to insert, a row into this table. And it returns saying, oh, the row was inserted. Then insert another row, the row is inserted. Well, we extended the language so that we can say, like, okay, insert the row, but kind of do it asynchronously. You don't have to tell me if it succeeded or failed. I'll figure that out when you commit. And this allows us to do a bunch of inserts in parallel. There's also stuff that's kind of built right into the SQL language. You can do inserts of multiple rows at a single time with a statement. And we take advantage of that, and we encourage users to use that when possible. It's called batching. So we encourage batched operations are possible because the batch operations allow a lot of parallelism. Well, if you're doing these things one row at a time, like each statement's operating on a single row, it just gets very slow, and you're hitting these geographic latencies and experiencing them much more than necessary.
And digging a bit deeper into the geographical capabilities of the database, I know that one of the things that it enables is to keep a certain subset of the data within a particular geographical region, which is relevant for some of the GDPR requirements and some of the various other compliance frameworks. So I'm wondering if you can describe a bit about how that works and some of the complexities that might entail in terms of managing how that data is located or joining in data across the cluster for certain queries.
Yeah, so I mean, GDPR, all these regulations, they're very interesting and intriguing to us because they're changing the landscape of what's necessary from your data storage system. So what Cockroach provides is we have this concept of a zone and a configuration for a zone. So you get to tag the tables in your database as being part of a particular zone. And the zone configuration says like, oh, for this table of data, I can specify which nodes in the cluster it can reside on. It doesn't force it to reside on those nodes, but you can exclude certain nodes in the cluster or, nodes in a certain geographic region, and you can include nodes in other geographic regions. And you can actually control this at a fairly fine granularity. How does Cockroach know about the geographic regions? Well, you have to configure it at startup. When you start up each Cockroach node, you give this command line flag that says, here's the locality. So Cockroach doesn't actually really know about the geographic regions. It just knows about you've given it a label to each of the nodes, and you can control where the replicas associated with the zone, where they reside, which nodes are allowed to reside on. So that was the original design of tables and zones, and we've since extended this so that you can take an individual table and you can partition it. There's a variety of mechanisms for partitioning it, but just imagine you're partitioning it. You partition it by the primary key. So you can have ranges of data within a table itself and say like, oh, here's my user data for users in France. I'm going to restrict that to the France zone. And here's my user data for users in the US. I'm going to restrict that to my users in the US. And the two benefits here are there's a regulatory benefit. GDPR or some other regulation might require you to do this. There's also performance benefit. If your users are in the US, you don't want their data to be in Europe and have to do a transatlantic crossing for every access. So that's where we are right now. Our primary focus so far has been where the data physically resides. So far, the regulations and what we provided haven't talked about, where we actually are allowed to process the data, but that stuff's all coming down the pipe as well. Being able to control and say the data must not leave this particular region, something we're thinking hard about. We'll be providing controls on that probably in the future.
Going a bit more into the implementation of Cockroach itself, I know that at least initially, and I'm assuming this is still the case, it was written in Go, which at least traditionally is a bit of an unconventional language choice for building a database. So I'm wondering what you have found to be the pros and cons of that choice and whether you've been happy with it.
Yeah, that's a good question. I mean, it's untraditional in that traditional SQL databases haven't been written in Go, but a lot of the NoSQL landscape, a lot of the Hadoop landscape was written in Java, and there's a lot of similarities in kind of the performance, runtime performance between Go and Java. When I was at Google, I actually was something of a C++ guru, and I used it for 10 years of my time at Google. I kind of loved the power and control of C++, but I also had a lot of frustrations with it. It's super easy to write code in C++ that your future self cannot understand, let alone your coworkers. My experience with Java was one of frustration fighting the garbage collector when performance tuning it. So Go is also a garbage collected language, but it provides significantly more facilities than Java for controlling memory allocations and memory layout. That's been kind of important. My experience using Go is that we're able to use those facilities that when there are issues with the garbage collector, we can work around them. Having said that, though, there's still ongoing frustrations. The Go GC, every now and then we've encountered issues where it does something surprising. It's caused increased latencies, has some peculiar behaviors. But overall, I'm fairly happy with it. And so that's kind of at the low-level kind of runtime of Go. If we step back up level and think about what's it like to program the language, Go doesn't have the bells and whistles of C++ or Java. I mean, the big notable exception is there's no templates or metaprogramming. And I see a lot of new engineers get frustrated by this. And frankly, when I initially started using Go, I had a bit of that frustration as well. I used templates all the time when I was at C++. I was very good at using them and decoding the compiler errors. You don't have to deal with any of that in Go. Go compiles super fast. It has this focus on simplicity, which is fantastic. The Go code I wrote 6 months ago, the Go code I wrote a year ago, is still perfectly understandable. Sometimes there's a little bit of additional verbosity to it, but I will happily take that trade-off. And one of the things we notice is, Go, it's a small language and you can pick it up super quick. I mean, most of the engineers who come to Cockroach Labs, they either have minimal Go experience or no Go experience. And you really, after a week, they're doing, PRs in language without problem. After a month, they're proficient. And it takes a few more months after that to kind of learn, some of the smaller bits and pieces of the language. But it's really super easy to pick up. And I contrast that with something like C++, where you can work in C++ for years and still not know what's going on under the hood. And there's another language out there that's, kind of hot nowadays, which is Rust. And I don't personally have experience with Rust, but everybody who does talks about the steep learning curve of trying Rust. It's kind of like an open question, though. If when we started working on Cockroach, Go was kind of ready for use and Rust was not. If we were to go back in time and Rust had been available at that point and was ready to use, would we still have chosen Go? I don't know. I just don't know enough about Rust to know the answer. Another question is now Google's released some C++ libraries that make programming in C++ much more pleasant. Could we, have written Cockroach in C++? Certainly. I'm just not sure if the trade-off is worth it. It certainly would solve some headaches, but it would have caused a massive amount of additional headaches.
And I'm sure that it's also made your life easier in terms of distribution to end users, because one of the strong points of Go, particularly as an operations engineer, is that the binaries are easy to generate as statically linked artifacts. So you just drop it in place, give it a config file, and start it up without having to necessarily have a lot of system libraries linked in or system dependencies at deploy time.
Yeah, no system dependencies at deploy time. I mean, this is one of the kind of the architectural decisions of Cockroach as well. Something my co-founder really pushed for, which is he didn't want any other, us to really be dependent on any other systems. And certainly Go is part of that. There are no shared libraries that we're linking to that you have to deploy and whatnot. And it's kind of interesting that, we took that push, and Cockroach itself is a single binary. It's super easy to get onto your machines and push around. And now we have this whole container ecosystem, which kind of gives you a little bit of the same flavor. And what, from our perspective, I love containers using Docker for doing certain development tasks is awesome. And yet when you toss Cockroach into a container, it's not really, the container does something for you, but it doesn't do too much. I mean, in comparison to running some like Java app inside the container, where the container is like taking care of getting everything set up with the environment, and your Java app needs that, Cockroach doesn't need that. So there's all this stuff that the container provides that Cockroach doesn't utilize. For the most part, if I'm advising someone to try running Cockroach, I'm like, just use the binary, don't bother with the containers. You're just adding another level of complexity there.
And looking at the documentation, though, one of the things that, because of the easy scalability and easy distribution of Cockroach, looks like you're also strongly in favor of deploying it on top of Kubernetes, because that's a widely regarded and widely available deployment target that people are focusing a lot on these days.
That's correct. We have a lot of customers coming saying, like, how do I run my database on Kubernetes? And a lot of traditional databases, they don't want to. There's a little bit of a mismatch there. It's so easy to horizontally scale out your application using Kubernetes, but you don't get the similar benefit from your database because your database isn't horizontally scalable. And we feel there's a really nice fit there between Cockroach and Kubernetes, where you want the stateless application to be horizontally scalable. You also want your stateful database to be horizontally scalable, and Cockroach works well there.
Just to spend a couple of minutes talking about the CAP theorem because of its prevalence when discussing databases. Looking through the documentation, I know that Cockroach, in terms of that framework, is strong on the consistency side. And so there's a debate of how it manages to be, in some regards, both consistent and in some regards also available. So I don't know if you want to speak to that or just point people to the documentation.
Yeah, I mean, I would point people to the documentation. I believe we might have a blog post about exactly this topic. But the summary is we're consistent, and in the face of partition, the CAP theorem is kind of confusing. I mean, what it's saying is consistency, availability, partition tolerance. You can have 2, you can't have 3. This is proved. But another way to think about this is, okay, in the absence of network partitions, what happens? And Cockroach is consistent. When there is a partition, what happens to the system? And when there's a network partition, Cockroach is still available, but only on the majority side of the partition. So this makes Cockroach a CP system. A system which is available, an AP system, is one that when there's a partition, both sides of the partition are available. But one of the things you get into with these AP systems is that the availability at that point you might have inconsistencies in your data. Clearly, one side of the partition can't talk to the other side of the partition. They don't know what they're doing. You could have two users withdrawing, money from the bank account. That would be the nightmare scenario for a bank. So for a variety of data storage systems, you don't want that availability. You actually want to shut down and not try to stumble forward in those cases. And that's the trade-off that Cockroach makes, is we're saying, hey, we're going to maintain consistency at all costs. We're not going to allow you to get your bank accounts into an inconsistent state.
For people who are coming to Cockroach from either NoSQL databases or traditional SQL databases, what have been some of the common points of confusion that people come to you with when they're first getting started with it or working on operating it?
Yeah, so a pretty common point of confusion is just about how our replication works. It's very easy to think like, oh, hey, Cockroach, replicates the data. So I'm going to start up 5 nodes, and the data is going to be replicated to all 5 nodes. And each node is essentially an identical replica of the data. And that's not how our data model works. Our data model is that we take all the data, it goes into this monolithic key space. It's divided into 64 megabyte ranges. And each of those ranges is replicated, but it's not replicated to all the nodes in the system. This is where you specify the replication factor. So let's say you have 5 nodes in your cluster. The default replication is 3 ways. So there's going to be 3 copies of the data, and they're going to be spread across the cluster. And just like having that mental model that, the nodes are not replicas of each other, but the replicas are down at this range level, and those replicas are then spread across the cluster. I think that's one of the more common sources of confusion.
And are there any particular edge cases or failure modes that people should be aware of when they're working on getting started with Cockroach?
I think the edge case that comes up is that we do value consistency over availability. Because we're using consensus replication, the consensus replication implies that in order to serve data, you have to have a majority of the replicas available. So let's just take a very simple example. You have 3 nodes in your cluster, and you decide to take 2 of the nodes down. Then there's only 1 replica left for each of your ranges, and Cockroach won't serve the data at that point. And you might be like, why can't it serve the data? Well, if you think through some of the scenarios that could have occurred here, this node that's still up, it doesn't know what happened to the other 2 nodes in the system. And because it doesn't know what happened, it might have stale data. And Cockroach is erring on the side of consistency. It doesn't want to serve that stale data. It doesn't want to allow that data to be written to, because if that data was written to, then perhaps the other 2 nodes come up, and this node that was alive goes down, and then suddenly you got more and more inconsistencies in your data. And I think this kind of, it's not really so much of an edge case, it's kind of a fundamental property of Cockroach, is you need a majority of those replicas to be available in order to both read and write the data. As long as you're like, you have the right mental model, users, can then, they're aware of this, they can understand, they can work with it. But very, it's kind of like the first impression is like, oh, I think of this as just kind of like, primary, secondary replication between MySQL databases, between like a MySQL database. And in those cases, like the primary goes down, I can just read from the secondary. There's, secondary goes down, the primary is unaffected. And for consensus replication, it just doesn't work that way.
One of the main factors of Cockroach is, again, the SQL interface, and reading through the documentation, I noticed that the syntax is primarily modeled after PostgreSQL and with some exceptions. So for somebody who has an existing application or is using an ORM that supports PostgreSQL, is it possible for them to point to CockroachDB and use it in the same manner? And what are some of the examples of differences in syntax where either Cockroach has extensions that aren't present in other systems or is missing some of the extensions that somebody might expect in Postgres?
The answer is, maybe. Maybe it might just work out of the box. We try to adhere to the base of PostgreSQL. And by the base, I mean the stuff that's part of the standard, SQL, part of the SQL standard. Examples of things that are outside the SQL standard that Postgres supports that we do not: full text indexes, any of the plugins, geospatial indexing. There's also some kind of more esoteric bits of the SQL standard that we just haven't gotten around to supporting yet. But most of those esoteric areas are not something that your typical application will run into. But you also asked about ORMs, whether the ORM will work unmodified. And this is an area we're actively working on, because while we do support like a large swath of the SQL, PostgreSQL, And we actually support a large swath of the SQL used by ORMs. ORMs themselves, when they start up, they do a lot of this introspection of the database. And in order to do that introspection, they use these kind of two bits of functionality. They access something called the information schema database, or they access the PG catalog. And these two, the information schema and PG catalog, they're essentially the same bits of data presented in different ways. PG catalog is Postgres specific. Information schema is something related to the SQL standard. But they allow you to essentially reflect on the data in your database. Tell me what the tables are. Tell me what the types of the columns are and whatnot. And we're still working through compatibility at that level because the ORMs require, they seem to touch every nook and cranny of what Postgres provides, the various ORMs do. So while we might support everything needed by one ORM, a different ORM has a certain set of queries that it runs at startup. These aren't queries that are executed by the application, but the queries executed by the ORM when it connects to Cockroach. And we're still working through providing compatibility for all of those. And lastly, you asked about extensions, bits of SQL that Cockroach has added that aren't part of Postgres. Some examples of this is we have this concept of interleaved tables. So if you have two tables that are related via parent-child relationship, and this might be something you normally express via foreign keys, we can actually specify that the child is interleaved in the parent. The purpose of this interleaving is it actually co-locates the data. Normally, if you have two tables in Cockroach, their data is on different ranges, and there's no overlap, there's no co-location of that data. And by doing the interleaved, using the interleaved syntax, you can actually tell Cockroach, hey, this data is going to be accessed at the same time. It should be right near each other. And if it's right near each other, it's faster to access. Another example of an extension is that bit I mentioned earlier in the podcast relating to being able to do essentially async operations and then waiting for them to commit when the transaction is committed. And this is via kind of an extension of Postgres syntax. Normally in Postgres, if you do like an insert statement, you can say insert returning some column. Well, we allow you to say insert returning nothing. And when Cockroach sees that, it asynchronously executes the insert. And then when you go to commit the associated transaction, it waits for all those asynchronous operations to commit.
Have there been any particularly interesting or unexpected uses of Cockroach DB that you've seen?
I mean, the one I'm, kind of excited about is this everything regarding GDPR and what's coming up there, the geographic use cases and how the regulatory environment has kind of opened up this opportunity for us in the industry, and it's causing everybody to think their data storage. I don't know if there's any I can talk about in particular other than, many companies are concerned about this, and it seems to be an increasing concern, especially with GDPR right on the horizon right now and just going forward. Everybody's moving into these, even some relatively small companies are kind of going global before you would expect it and needing these global storage requirements.
Yeah, it's definitely interesting seeing the reaction that people are having where some people maybe only focus on a particular region and so they're largely unaffected. But yeah, it's strange the distribution of size of company and type of company that are being affected by these new regulations.
Yeah. There's actually another kind of interesting use case for Cockroach, and it was a little bit unexpected to us, which is we have a number of users using Cockroach due to kind of the ease of automation. And what I mean by that is if you were to use something like MySQL or Postgres, those would be the natural choices for a relational database, but you want to essentially embed those databases into your own product. You want to naturally set up replication and failover and whatnot. And there's, doing that in kind of an automated fashion is challenging. With Cockroach, it kind of naturally has that automation and failover capacity built right into it. So there's a handful of users who are using in this case where they're essentially, embedding Cockroach into their systems. And they're doing this because it provides the SQL functionality that they could have gotten from MySQL or Postgres, but it also provides the reliability. And it does this in a fashion that's kind of a little bit more hands-off for them to administer. They don't have to worry about the failover. It just kind of comes for free out of the system. And the thing that I think is fascinating is we initially designed Cockroach about for these huge systems of scale, but this use case isn't one about scale. It's about ease of use, ease of automation.
So it's starting to edge into the use case where people might use a SQLite database because of the fact that it's easy to just instantiate it and not have to worry about it. But they also want to have this capability of networking these various components together without having to worry about all of the additional logic that's necessary to do that with a SQLite database, for instance.
Yeah, I mean, I'm not even sure how you would set that up with SQLite. SQLite is just, it's an embedded SQL database that you're putting into your application. Cockroach is a little bit more of you're embedding into the product, not into the application. And it is giving you that redundancy for free that I'm not even sure what you do to set up SQLite to provide redundancy in the face of node failure.
Yeah, nothing fun, I'm sure.
And nothing. There'd be a lot of work at the application layer or just additional work in your product to achieve that. And that's kind of what Cockroach is doing. So just use Cockroach instead.
And are there any particular use cases where Cockroach DB is the wrong choice for somebody?
I mean, I think the broad class of use cases where Cockroach is not a good choice right now and probably won't work well for you is when we think about analytics use cases. If you're ingesting large amounts of data and then trying to perform analytic style queries on this. This is, systems that do this like Vertica, like, Apache Spark, they're designed for this, super high throughput, these long running queries. They have sophisticated optimizers for optimizing the queries. And this is just not an area that we focused on in Cockroach. And because we haven't been focusing on it, when we've done some testing here, it's not performed as well as you would get from these other systems. Our focus so far has been on transactional processing. We want to be that, the database of record. We've taken care, all our concern about consistency and isolation. These all play into the transaction processing space where they can be important for analytics, but usually they're a secondary concern for analytics. Analytics is primarily concerned with just raw query processing speed.
And are there any new features or a general direction that you're hoping to see Cockroach go in the future?
It feels like the longer we work on Cockroach, the more stuff we want to add to it. General features, we're just going to be enriching the experience for transaction processing. Some of the stuff about analytics, we're going to be edging in that direction. The next release of Cockroach, which is scheduled for this fall, is going to have a much more advanced query optimizer. And this is going to be getting our initial footsteps into some of those analytics spaces, though I don't think we're going to be moving too far in that direction. And then there's, I think the big one that's coming out in this next release as well is something called change data capture. And this is a way of streaming data out from Cockroach. You can essentially subscribe to a list of changes to a table or a set of tables and stream it out via Kafka. And we've had an immense interest from users for this feature so that they can, essentially get data from Cockroach, which is being used as a transactional data store, and get it out via Kafka into their analytics system.
And have there been any particular challenges of building or maintaining the technical or business aspects of Cockroach?
It's a little bit of a broad question. There's challenges all over the place. Whenever you're building one of these systems, there's enormous numbers of moving parts, and you focus on one area and another area doesn't get as much love, and you're trying to lift the whole system up at the same time and get to a state of usability. And the initial struggle of the first 2 years, I would say, at the company was getting to that broad set of usability. You're trying to find that minimal viable product, but for a database, the minimal viable product is actually pretty large. That's one of the challenges we've experienced. One of the ongoing challenges is the SQL standard is large, and it's like the surface area of all the functionality provided by a SQL database is just huge. We have to be both prioritizing what we do and making choices there such that we provide aspects that our current set of users are finding useful, but while also looking to that next set of users that are missing little bits of functionality.
So for anybody who wants to follow up with you or follow the work that you're up to, I'll have you add your preferred contact information to the show notes.
Sure.
Thank you for taking the time to join me today and the work that you're doing with Cockroach DB. So I appreciate that, and I hope you enjoy the rest of your day.
Yeah, it's a pleasure chatting with you. Take care.